This is work done in collaboration with colleagues from the IBS Center for Climate Physics in Busan and also colleagues from the Gangwon National University. So the talk will essentially introduce you into how we obtain data on abrupt climate change that occurred during the last glacial period. Why the last glacial period? It's the time when we see the largest instability in our climate system. And the data that we are extracting are actually from Korea, not far away from here, about 150 kilometers away from here is a cave that tells us an interesting story. But the story is not only about Korea, about something very regional, but the story is about something that happened in the North Atlantic. And I would like to share these results with you today. So a little preamble here. We talked first about water isotopes. As you know, water comes in different isotopes. We have the H216O, the dominant one, 99.7% of our planet has that isotope. But we also have heavier isotopes. For instance, we will focus on the H218O. Wow. And that's about 0.2%. But depending on which medium you're looking at, for instance, water, ice, or rain, you will find different ratios of these isotopes. And this is usually characterized by the delta 18O. This is the measurement of the fraction of the heavier one to the lighter one in a sample divided by the same fraction in the standard. And the standard usually is ocean water. We subtract 1 and we multiply with 1,000, and then we get numbers as demonstrated here in the bottom. The ocean seawater is very close to 0 per mil. Rain typically has about -7 per mil, and ice has something like -20 to 40 per mil. So these are indicators of phase transitions that actually happen for these water pathways in a process that is referred to as fractionation. And fractionation is the isotopic sorting during chemical and in particular physical or biological processes. So I will introduce this a little bit more here. Think about it as the hydrological cycle traced through the lens or perspective of water isotopes. Water in the ocean has about 0 per mil. As it evaporates, the heavier water stays in the ocean, so that one that has a higher value of the higher percentage of the 18O. Light, so we have delta 18O in the water vapor that is depleted. It has -10 per mil, and that water vapor eventually gets transported in the atmosphere. As it condenses, a part of it gets precipitated out. The first rainfall might be -3 per mil. As we are pulling out water with -3 per mil, the water vapor itself gets further depleted to -13 per mil. We have a precipitation, another precipitation event, for instance, with -10 per mil. And then you can see the more precipitation events, the longer the pathway in the atmosphere, the more depleted the water vapor will become, and also the more depleted along this trajectory the water isotopes of the precipitation will be. So if we drink tap water outside, for instance, we would see typical values of -7 to -9 per mil. So this is essentially a proxy of the pathway, the atmospheric pathway of water vapor in the atmosphere. And how can we use that to understand climate change? We'll come back to that. But first of all, let's, in order to understand our data that we obtain from a cave in South Korea, we first need to ground truth. We need to benchmark essentially what we have under present day conditions. For that, we have a number of high schools in South Korea that collect water samples for us, monthly water samples, and we measure their isotopic composition in our lab using a laser ablation, a laser water isotope analyzer. And this is just the mean rainfall over Korea. So you can see strongest rainfall occurs here in summertime, the so-called Jangma rain, which is the East Asian summer monsoon. And if we look at the isotopes of the water coming from this rain, we see that the typical value of -7 is much more depleted in summertime as compared to the winter. What that means is that, as you saw, the more depleted these values are, the longer the pathway, the water vapor pathway in the atmosphere is. And this means that the water that actually precipitates in summertime comes from farther away. Actually, well, it comes from the tropics rather than from more local sources. That is important because we can learn something about isotopic fluctuations as a proxy for atmospheric circulation states. Okay, little preamble number 2 on abrupt climate change, a few words. These two gentlemen, they looked at paleoclimate data. Willy Dunsgaard in particular looked at ice core data from Greenland. And again, they measured the delta 18O of the ice in Greenland going back to 60,000 years. This is present day. And what they found is that during the last glacial period, which is kind of this period here, there are large fluctuations in the climate system. So suddenly the climate system flickers, jumps to another state with temperatures about 7 to 8 degrees higher over Greenland. Here's the last glacial termination. We are entering our relatively stable Holocene phase, and that's where we are right now. So these phase transitions, these rapid transitions have been interpreted as changes in the temperature of the last phase transition, the transition from water vapor to snow. So this is essentially a time evolution of temperatures over Greenland. And the variability here is referred to as Dunsgaard-Oeschger variability. And these are some of the largest and most rapid abrupt climate changes that our planet has experienced. And what you can clearly see is that these transitions, they are typically very rapid when it comes from going to cold state to warm state. And then you have a sawtooth-like behavior, cooling, bringing you back to the cold state again. That's going to be important for later on. So it's a pretty complex signal, as you can see, highly non-stationary. There is no clear periodicity. You have this sawtooth structure, and there's also this also reveals something about the underlying physical processes, which we'll talk about later on. Now, if we look not in the ice cores, but in sediment cores, mud cores, essentially taken from the ocean, you can see interesting rapid transitions as well. For instance, this is a sliced sediment core from the North Atlantic. And in the middle of the North Atlantic, suddenly you find these sand grains. How on earth is sand entering the North Atlantic suddenly? And then you have another layer right above it, which is the typical microfossils that you find in the ocean. This is stuff that lives at the surface, eventually dies and falls down to the bottom where it accumulates in the sediment. What explains these rapid transitions? Well, the idea here was that, in fact, they come from the last glacial period when we had a major ice sheet, the Laurentide ice sheet over North America, and every once in a while you have an instability of this ice sheet, which sheds off these icebergs into the North Atlantic. And as this typically the ice sheets, they sit on the ground and they carry a lot of material. You can see that nowadays even in icebergs. And if you have lots of these icebergs over several thousand years, you're starting to accumulate these gravel or sand layers in the deep ocean as well. So this is kind of the interpretation of these so-called Heinrich layers. Now, what's interesting is these abrupt transitions, some of these abrupt transitions where you see you start with a cold state and then it jumps back to a warm state, they occur usually just after these so-called Heinrich events. Heinrich events are periods where we have massive iceberg armadas in the North Atlantic, which means also they're starting to melt. They dump fresh water into the North Atlantic. And Henk Dijkstra talked about the shutdown of the circulation in the Atlantic. In fact, we have clear evidence that these periods where the icebergs broke off from the major ice sheets are also periods where the circulation collapsed in the Atlantic and where we had corresponding cooling. And that's why we have these cooling periods. Okay, so this is setting the stage. Let's come to the main story. The main story starts in a small cave called Jungmal Cave, not far away from here. This is a very difficult cave to access. And the story is just about a tiny little piece of rock. But that rock, essentially, calcite rock, explains a lot of things about the functioning of our global climate system. And you can see one of our postdocs climbing down in some of these caves. In our lab, we have a team that analyzes these rocks. using geoisotope analysis tools such as isotope ratio mass spectrometry. All right, so let's take a look inside a cave. You remember probably from high school, there are stalactites that go down and stalagmites that come up. We only look at the stalagmites because they grow better. Inside a cave, well, I'm sorry, go back. Inside a cave, we have, there is a hole here, there is a cavity, and water from the surface, from the rain essentially, trickles down through the soil, trickles down through this so-called epikarst layer, which typically is limestone. And the limestone partly gets dissolved by the action of the water, and there is also CO2 itself in the soil, and that starts to dissolve the limestone. That dissolved limestone essentially in the water drips back into the cave where it can reform limestone. And these are the stalagmites and stalactites, which we commonly refer to as speleothems. Okay, so just the reaction now. What does it all have to do with the isotopes? Well, we have the isotopes of the rain, the delta 18O that I mentioned earlier on, about -7 per mil typically. That drips into the cave, and a part of this drip water, most of the drip water actually includes still the isotopic signal from the rain. However, then as the calcite forms in the cave, again, from the drip water, actually the temperature in the cave itself also imprints on this calcite delta 18O. So we have a transition from the water delta 16O, delta 18O into the calcite. So by measuring the calcite isotopic composition, we can learn something about two things: the original water isotopic composition of the rainfall, as well as the temperature in the cave. So this is a way of reconstructing climate from stalagmites. And a typical stalagmite looks like this. We cut it open, we polish it a little bit. And as I mentioned earlier on, think about it, we have climatic factors, rainfall, atmospheric circulation. They generate anomalies in the rainfall that becomes drip water in the cave. And part of this kind of enters up in the isotopic composition of the calcite itself. Okay, and the other process was the air temperature outside the cave essentially drives the changes inside the cave as well, which also imprint themselves on the delta 18O of the calcite. So this machine, isotope ratio mass spectrometer, measures for little samples along the growth axis of the stalagmite the delta 18 of the calcite, which will allow us to learn something about the climate states in the background. We also need to date how old is this stalagmite. For this, we use uranium, thorium age geochronological methods. They're not available in Korea, so we send the data usually to China. Okay, so think about it. The last glacial period, there were major ice sheets over North America and also Eurasia. So the sea level was lower because water from the ocean was moved on land as ice. So 120-meter lower sea level means China and Korea were connected. The Yellow Sea or West Sea was essentially just a land bridge. So I'm always teasing my Chinese colleagues, saying it's clear that China used to be part of Korea. But so this is the situation which also we need to consider. There is no water here. The cave is called Jungmal Cave, and this is the little, if you like, calcite speleotherm, the rock sample cut through, and you see some nice growth bands in here. It's not long, it's about 30 centimeters in total, but it captures the time evolution of climate over the last 30,000 years. And so we sampled along the growth axis. We have a relatively good age model, different quantities. Let's start first with the delta 18O, as I mentioned earlier, from this Korean sample in orange. Time goes from right to left, and what you're seeing is that here suddenly there is a change in the delta 18O. As we know, it could be either temperature or rainfall. We don't know yet. We need to figure that out in more detail. Then there is a relatively stable period. We are looking at the last glacial period. We're just about to come out of this glacial world into the interglacial world of the last 10,000 years. And then there is another event where suddenly also we have actually what looks like a drop is in fact an increase. So I draw the axis usually the other way around. We have an increase in the delta 18O and another one here. And this is the one that I would like to focus on in this talk. This is happening around 16,000 years ago, and it's called the 16 Ka event, kilo years, kilo annum. And it is one of the fastest climate events that demonstrate a cooling on our planet. Actually, the initial transition happens within 5 years. So we have evidence that this is extremely abrupt. And we can see it corresponds, or it happened during a time period, the so-called Heinrich I event. Heinrich I, you remember, were these layers of sand that correspond to a shutdown of the overturning circulation and these armadas of icebergs in the North Atlantic. And this is Heinrich II. So you can see whenever something happens in the Atlantic, the circulation shuts down. We have anomalies also over Korea. Now, there has been another record from nearby, from China, Hulu Cave, which shows exactly the same behavior. So we are not looking just at a regional feature, but we are looking at something that is quite reproducible. And also the amplitude is pretty much the same. Now, if we compare this time series, this abrupt time series with other data, what we see is actually, this is an index of the Gulf Stream strength, the Florida Strait transport, so this green one here. And you can also see, even though it's not very well, it's hard to move this mouse, is not very clear, we see there is a weakening of this Gulf Stream transport that happens already before this major event around 18,000 years ago, but during the event we have the absolute minimum. So clearly something is going on in the Atlantic that we pick up over Korea here for the very first time. And we can also look at the amount of this iceberg sand, if you like, iceberg rafted debris in the North Atlantic from this brown record. And you can see also it starts to go up a lot earlier, about 1,500 years earlier, and then it peaks around 16,000 years ago. So the Atlantic is doing something. There is a major reorganization in the climate system, which is being picked up by the East Asian summer monsoon, both over Korea and China. Okay, well, what else? So it turns out, if you look closely, and that's something that people haven't done so far, you see these events, the same event also in other cave records. For instance, from cave in Spain, Ostolo Cave. But there, the anomaly goes the other way around. There we have this massive, what goes up is actually negative here, a massive negative anomaly, and so on. So interestingly also, if you look at records from Brazil and also Australia, there is something cooking that's suggesting there is actually a bipolar or interhemispheric seesaw of some sorts. I will show this one again. The red record is actually from Brazil. And again, you see there is a major event occurring during this time period. So what happened? We need to dig a little bit deeper into this. And that means that I have to introduce the so-called clumped isotopes. These are isotopologues of calcium carbonate. And also keep in mind, we talked about isotopes. So we have the 16O and the 18O of the water, which is kind of embedded in the calcite matrix. But we also have calcite is calcium carbonate. The carbonate has a carbon in here. And it also comes in 3 different isotopes. We only focus on 12C and 13C. So by looking at the relative ratio of these isotopes, we can actually extract directly the temperature. And that's something we can call PaleoThermometry. So by measuring across this transition, the clumped isotope ratios, we actually have a real indication of the temperature. Again, this is a zoom into this event, as we saw before, from the delta 18O, which could be temperature and precipitation. Now the yellow dots here are really demonstrating the change an absolute change in temperature. What you see is that within 5 years, Korea cooled by 7 degrees Celsius, which is enormous. It would have had major effects on humans who lived here already. It would have had major effects on vegetation, mammals, the entire biosphere. So this is a very large scale event, and these can be further tested. But this seems to be the first indication of a massive cooling that occurred. And remember, the Dansgaard-Oeschger events that also take place within 5 to 10 years, they are rapid warming events. This is the first rapid cooling event that we're seeing. So what else can we do with this record? I call it Paleo Crime Scene Investigation, or Paleo CSI. We have another instrument in our lab that's just came new, but a similar instrument we used in order to analyze elements along this axis. I'm sorry. Along the growth axis, we can run a laser scan. So the laser burns off material, which is then analyzed in a mass spectrometer, and we can measure the trace elements, all the elements from boron all the way to uranium. And we will focus here on the rare earth elements. Of course, everybody having an iPhone or cell phone computers knows what they are and that they're geopolitically quite interesting. It turns out, if we look at these rare earth elements, the lanthanides, if we look at the sources, China, the Gobi Desert and Taklamakan Desert, they have preferentially more of these lighter ones, whereas the soils over Korea, they have a preference over, relatively speaking, for heavier ones. So by measuring the light to heavy rare earth element ratios, we can learn something about where the dust came from that was deposited in the cave. Did it come from Korea or from China? So this is just a result. I won't go into the details of the analysis of all the elements that we measure, from boron all the way to uranium. And what you can see is in the principal component analysis, there is clearly something happening at this 16,000 year event, which is nicely reflected also in the rare earth element concentrations. And in particular, if we come back to this 16,000 year event here, what you can see is, this is again the oxygen isotopes, here is the event. What you can see is that there is a difference between the rare and light isotopes. Very clear difference. And that one means, if we look at the difference in more detail, it occurs right here. Here's the main event. And it means that more dust from Korea, Korea or north of Korea, is getting deposited in the soils here. Whereas prior to that, 18,000 years ago, it's much more Chinese dust, which indicates that we have actually westerlies. So we do not only reconstruct changes in temperature and precipitation, but we can also see changes in the westerly winds here. Okay, so again, I mentioned there is something happening in the North Atlantic. If you look a little bit more closer at some of these sediment cores from the North Atlantic and the grains that are contained in these sediment cores that are indicative of iceberg rafting, you can see, well, clearly during this event, there is something happening. There is a rapid event. Where did it come from, and how did it create these anomalies across the world is the next question. Where did it come from? It's still speculative. There are possibilities that as these ice sheets, this is the Eurasian ice sheet here, 17,000 years ago, as they melt on the southern flank, because it's where it's warmer, they form these large proglacial lakes. They're enormous. They're as big as the Baltic Sea or even larger. And these proglacial lakes, they can essentially drain very quickly once they have an opening to the ocean, as these ice sheets start to retrieve, as you have these saddle collapses. And that could be a source, a rapid burst of one of these proglacial lakes that could explain a meltwater input within 5 years into the North Atlantic and the corresponding climate anomalies. So we try to better understand what's happening here by using our supercomputer Aleph next door, and this supercomputer was calculating a numerical simulation of the climate system. A typical climate model has about 1.3 million lines of code, and it solves the equations of momentum and radiation and other things of the atmosphere and also the ocean. So full fluid dynamic Navier-Stokes type of equations, as well as the full the radiation in the atmosphere. Okay, so what we did is we ran a climate model and we dump fresh water into the North Atlantic that mimics the effect of these data that we saw from the North Atlantic. And what we're seeing here is the delta 18O of this freshwater signal. So I'll run it again. And you see it's starting to get very negative for a few hundred years, 200 years, and then it kind of disappears. So this is the source. And you remember ice sheets have a very negative delta 18O, as I mentioned earlier. And as these ice sheets melt, they leave these glacial lakes that still have this very negative delta 18O water, and that gets dumped into the Atlantic. Okay, fine. That's the forcing. Now let's look at what the climate system does with this kind of high freshwater and the change in ocean circulation. Here are the temperatures. So you can see this event causes a massive 200-year-long cooling over the entire northern hemisphere. If I run it again, you can see in the southern hemisphere, it's slightly opposite, actually. There is a little bit more of a warming happening there. Then, if we look at the rainfall, global rainfall, these events, they cause massive drying in the northern hemisphere. And as we look at the delta 18O, as we would expect to measure it from caves, we can also see there are these massive changes. There is a dipole between the Himalayas and the northern hemisphere. And over Korea, actually, we have the anomalies, negative anomalies that we just described earlier on that were measured from our data set from this scary looking cave. Okay, so I won't go into the details, but the story is if we compare our model simulation on the supercomputer next door with the cave data that were obtained from caves all over the world, we find actually an extremely good match. So this is the simulated delta 18O of the calcite from the climate model in the back. And these are actually the signs of all the caves. And we see that the fingerprint actually is quite clear. So by combining the oxygen isotope data from the calcite in caves across the world, we can kind of fingerprint the mechanism. That's why I call it Paleo CSI. Okay, you can also do it in time. In blue, you see data records that were obtained from sediment cores and 3 different caves. And our computer model simulation is shown here in orange. So we can reproduce these features quite well if we assume that the anomaly was triggered by a massive meltwater outburst of glacial meltwater into the North Atlantic. Okay, so that seems to work quite well. We can also look elsewhere in the world. Something else, something interesting happens. For instance, let's take a look at this one. These are impacts that were seen in other data sets. The red time series here is the methane as measured in ice cores. And it turns out within the dating uncertainties, there is a massive spike in the methane concentration measured in ice cores during that event. And where does it come from? Well, if you have these major changes in the precipitation, as we saw earlier on in the simulation, they can induce changes in the wetlands. As the wetlands change, tropical wetlands mostly, you can have an increase in the methane concentration, for instance. And this is a global measure of the photosynthetic activity. Also, we see actually going down means more photosynthetic activity, less photosynthetic activity, and that is also illustrative of major changes in the vegetation system globally. So let me summarize here. Let's say we start off with our North Atlantic abrupt freshwater discharge, and the origin, let's say, is still mysterious, but We think it has something to do with the Eurasian ice sheet melting and proglacial lakes that formed to the south of it. This freshwater discharge, same as what Henk Dijkstra discussed in his presentation, reduces the density of the surface waters in the North Atlantic, which under normal conditions fall down and drive this large-scale overturning circulation. Now we have very fresh water, less density, so the water can't sink anymore, which means the entire heat transport into the North Atlantic region is also starting to reduce. As a result of this reduced heat transport, we have cooling, which affects the entire northern hemisphere, as well as the major monsoon and westerly systems, as we just witnessed from the changes in the Delta 18O and the changes also in the rare earth elements, which are indicative of major atmospheric circulation changes. Changes of tropical vegetation we can see in some of the other records from the ice cores and their isotopes of CO2 and methane. So with that, I'm I think I'm happy to take any questions. Thank you.
Thank you, Axel, for a fascinating talk. Yes, please. Chris.
Hi, thank you. So I'm wondering, these events of melting ice, is this something we can see today? Because we don't have that many glaciers around today, right? So there is nothing to be melted. I mean, maybe Greenland, but that's not that much, is it?
So, of course, we have the Greenland ice sheet and the Antarctic ice sheet. And the Greenland ice sheet, as you may know, is melting partly. There is intensified melting. It's happening from the surface, but it's nothing compared to the event that we are seeing here 16,000 years ago. And the reason is 16,000 years ago, we are seeing the last remnants of the ice sheets of the glacial period, and sea level was 120 meters lower. So over time, within 10,000 years, the 120 meters need to be refilled. So this is actually a much larger reorganization of the ice sheets as what we are seeing right now. The Antarctic ice sheet is much more interesting, the West Antarctic ice sheet, because part of that is underwater. So if you have warm ocean currents around Antarctica, they can start to gradually melt the ice sheet from below. And then there are also positive feedbacks that can lead to an accelerated demise of the ice sheet. So if we think about rapid melting of ice sheets and rapid contributions to the global sea level rise, the West Antarctic ice sheet is more interesting in that context. But we don't have any large proglacial lakes yet. So,
yeah, if I have my second question, I wonder what happens after this, right? Because you said this is like 200-year-long period of melting, but does it have some long-term effect? Let's say now the planet is globally warming, and then is this kind of a correction effect that will put it back to the cooling stage, or it just, you know, some abrupt change, but then it goes back to the to the mean?
So this event is an interesting case because we see how quickly the system can recover quickly, well, within 200 years. Whereas if we look at other paleoclimate records further back in time, we see it usually takes a few thousand years to recover. So here we have, for the first time, an evidence for a relatively fast recovery of the system to, well, still glacial conditions. So the baseline is a different one. So that can tell us something about also the sensitivity of the circulation with respect to freshwater forcings. And Henk Dijkstra was discussing it also. If you bring down the circulation, how long does it stay dead forever? Is it a multiple equilibrium state that you will not recover from? Or is there a reversibility? And on which timescale is this reversibility actually taking place? We have evidence here that the reversibility might be faster, at least under these particular glacial conditions, than previously anticipated from climate models.
Okay, thank you.
Thank you.
Here, there's a question. Jürgen.
Yeah, thank you very much for the great talk. I'm coming back to these very fast transitions. The accuracy of the paleo data are not so good. How can you infer these 5 years? Can you comment a bit about it?
Yeah. So first of all, this is the beauty of stalagmites. You can date them very accurately, much more accurately actually than sediment cores and ice cores through this uranium thorium scale. But the 5 years we know because you can see annual rings, actually annual growth, and you can trace the delta 18O change with these annual layers in the speleothems. We can't see them in our record, but one Chinese group was able to identify the number of annual bands that occur between the onset and the peak period.
This is really clear world record.
Yeah, and so it's, if you like, it's a world record for cooling, because Darmstadt Oeschger events, you have a world record for warming, but not for cooling. Yeah.
Thank you. Are there further questions? If not, let's thank Axel for a fascinating talk.
Thank you very much.